All right. The next speaker is Anima Anandkumar, who's the Brem Professor at the Department of Computing and Mathematical Science at Caltech. Anima, please take it away.
Thank you, and thanks for the invitation. Great set of talks that I was looking up in the agenda. So what I'll do today is to give you an overview of where AI is, what are the cutting edge developments, and also some of the frameworks that enable large-scale learning and data analytics, right? And I'll show some of the latest tools NVIDIA is building to enable this. So we need to think of both the algorithms, the frameworks, infrastructure, all together in a holistic way. And I want to emphasize how we can develop AI methods that are ideally suited for scientific applications, how to incorporate different kinds of domain constraints and knowledge, and at the same time have the flexibility of deep learning. So if you're looking at this deep learning revolution today, it's really a trinity, right? Because the algorithms have been around for a long time, but it's the availability of large-scale data and the large-scale compute of GPUs that enable this revolution. And indeed, in astronomy, the data is enormous, so it seems ideally suited for the use of AI methods, as we've seen in many of the latest research. And the parallelism of GPU compute, traditionally what was done with as HPC for traditional methods in astronomy can now also incorporate AI, and you can have this hybrid AI and HPC methods to bring all this together. And what I'd like to do is to break down any AI algorithm into three parts, right? So the data is what kind of data the algorithm expects, what kind of priors we are building in. For instance, if it's images, we are building in convolution, but the question is, can we build richer priors, either that is domain specific or even domain agnostic? And then the other aspect is designing the task and designing the actions if it is something interactive. You know, if you're doing reinforcement learning, you have to design the actions. If you're doing active learning, you have to decide what next samples to take. So this is how I'd like to break down any AI algorithm. And if you look at most of the deep learning methods today, they require large amounts of data, but also supervised data that requires expensive human labeling. So ideally, we'd like to move away from that. The priors are quite weak. I mean, lots of instances where you can easily fool a deep learning model by putting like small blocks, as this example, putting imperceptible noise. So the questions of how we can overcome such kinds of corruptions and perturbations, ideally with the use of better priors. And then the task design is also very simplistic in many cases. And this is not only having an impact on performance, but also potentially lots of societal implications, right? I want to emphasize this in any talk I give because this affects all of us. For instance, face recognition has been in the news a lot because there it's easy to see this bias. You know, if you're training on data sets that is excluding darker skin tones and then putting it in the hands of law enforcement, that can be a dangerous situation. So this question of how to evaluate tasks, how to train for them, and the real world implications that has is something that the community is beginning to grapple with more seriously than before. And this is then needed to also think about new algorithmic development through task design. Yeah, so what I see are the next frontiers in AI is first focusing on unsupervised learning or semi-supervised learning, self-supervised learning. So going beyond anything that reduces the massive labeling requirements. And in many cases, the ground truth is not even known, right? Especially in astronomy, you may be wanting to do discovery rather than having ground truth labels. So these aspects of how to do good disentanglement learning, how to disentangle various features that are either through semi-supervised or unsupervised learning is important. and how to learn new concepts and compose them. So we humans are really good at conceptualizing entirely new entities, right? And a child that has never seen a dolphin, seeing it for the first time will still know it's an aquatic being, and it can swim, it has eyes. So these aspects, how do we build that into AI methods? So we've been doing quite a bit of work in this area. I won't talk about it here, but I can give you pointers. For instance, we've been doing disentanglement learning with the use of small amount of supervision in style GANs. So being able to generate high quality, realistic images, but also having the ability to control and disentangle them. We released a new benchmark called Bongar dataset that establishes a new way to test how good are concepts learned by deep learning methods. So you cannot just overfit and memorize on a data set. This challenges the models to actually learn them and evaluate them on new problem instances. So that's something that the current deep learning methods fall short of, but challenges like that are also important for us to then evaluate how good are these unsupervised learning methods, because you can't just evaluate them in terms of standard accuracy when you don't know the ground truth. The other aspect is priors. How do we build good, robust priors? I think we can take a lot of inspiration here from neuroscience, from the way our brain works. And in one of the projects in collaboration with Doris Sau at Caltech, who's a neuroscientist, we are asking how, the way the brain has feedback to get perception. So essentially the brain is hallucinating before deciding on what's the thing the eyes are seeing. Can we build such feedback into our feed-forward networks? And we've seen really promising results in terms of robustness by adding feedback to any feed-forward neural network model. And the other aspect I'll go deeper into in this talk is how to use different kinds of domain knowledge. For instance, if we are now solving, say, partial differential equations, we have these constraints, right? How can we enforce them, and how can we learn better through the use of that information? And lastly, indeed, we need better task design that can go beyond just a single task and single domain. So that was an overview. As I mentioned, a lot of our research is focusing on how priors are so important. The work we are doing at Caltech in having to land drones safely, but as well as at a high speed, how to do very careful trajectory tracking close to the ground. Those require blending the knowledge of physics, through traditional controllers and adding deep learning models and still retaining safety and stability requirements. The use of graph neural networks are natural in many cases. For instance, in a project with Tom Miller, who's faculty at Caltech, we have designed what's known as OrbNet, which combines molecular orbital features and graph neural networks to get the best quantum energy calculations with a 1,000-fold speed up. And today I'll go a bit deeper into the use of tensors for modeling any kind of multidimensional, multimodal data with complex correlations. And indeed, a lot of data that you may encounter have these properties. And tensor is an extension of a matrix to higher dimensions. So just as matrix has rows and columns, you now have many more dimensions of an array, but also like a matrix, you can multiply, you can think of low rank structures. Similarly, in tensors, you can contract or manipulate the tensor in different ways. You can also ask about low rank representations of a tensor. And by thinking about low rank representations, we can now capture rich multidimensional information without in a compact model. And that's the power of tensors, that they can incorporate a richer family of representations compared to just low rank matrices. And TensorLi is an open source framework we've been developing at NVIDIA. Jean Kosefi, who's the primary developer, is at NVIDIA. And what that does is provide ready-to-use tensorized neural network layers where it's a drop-in replacement to the current matrix layers, and also other core operations and decompositions with tensors. So it's written in Python. It has multiple backends if you're using NumPy or QPy for, say, more on the data analytics side, or PyTorch for deep learning, or even the upcoming JAX. So you can use the same front end, and there are lots of useful notebooks to get started on this. So I encourage you to go check it out. To give you an example application of how to replace matrix layers with tensors, a popular low-rank form is known as CP decomposition, so where you can express a tensor as sum of rank 1 components. And so in 3D convolution especially, it's very expensive to run, as the models are also now getting larger. And the question is, can we instead do separable convolutions and still get a good performance, right? So can we retain the performance, but do a low rank representation for a more compact model for speed ups? And that's where the TensorLi enables CP decomposition very simply, just using fit operations similar to the scikit-learn. And what we've seen here is that the model is extremely small compared to the state-of-the-art model, but also better performance. So bigger model is not always better. And what we've seen consistently with tensor method is that a smaller model, that because it captures the right multidimensional structure and the right correlations, is actually better. It's better generalizable, it's more robust, and it is compact. So you get best of multiple quantities using tensors. And we've also seen this with spatiotemporal data, which in astronomy, there is lots of such data sets available. And the idea is, if you're looking for more long-term prediction, not just the next frame or next few frames, but much beyond, that's where higher order correlations in data matter a lot. And what we built was this STM with tensor trains, which takes the hidden state frames, but further looks at the higher order correlations among them. So if you're taking a window of frames and looking at the higher order correlations, that is like a higher order Markovian model. But that's too big, right? You cannot directly express the higher order correlations. And that's where we can further decompose it as a tensor train, which is a low rank decomposition. And it's like a chain. It kind of is also retaining the causal structure in which these representations are moving. And by doing that, we can then have a model that can do early activity recognition very well. So you can see in this activity data set, the convolutional tensor train LSTM was able to detect the activity much early on compared to the other models. And in a variety of data sets, what we've seen is consistently the model is much smaller compared to a better performance. In some of the other data sets, we've seen good quality long-term video prediction, whereas having also a small model. So that's what tensors enable, having the ability to now replace matrix computations with higher order tensors that can better capture multidimensionality, that can better capture our ability to incorporate all the information effectively. Another work I want to quickly demonstrate to think about having domain-specific physics constraints, but also be able to do an efficient high-resolution model is this MESHFREE-FLOWNET. And here we are going to use the Rayleigh-Bernard equations of fluid flow. And the idea is reduce the computation cost immensely, but retain the accuracy. And so you see here the ground truth, the low resolution, and it's able to do the high resolution model prediction very well. And it's also constrained by the physics. So it's retaining the physical validity while being able to do the super resolution. And the idea here is that it's also mesh free. So it's resolution independent. So you can query the point at any location and you can get an answer, right? So it's not tied to the resolution in which it's trained, because we have this continuous decoder that can now make it resolution independent. And then the PDE constraints also help us deal with the ability to do the super resolution very well. And so that's an example of having the physics constraints added to make the super resolution problem be much more amenable, even at high Rayleigh numbers, which are the important measure of like turbulence. And also scalability, we trained it on 128 GPUs and be able to do this well. So lastly, I want to quickly mention Rapids as a way to do data analytics very efficiently. So in any AI workflow, most of the research focuses on like, okay, how do I train my model better, right? Including the work we've been doing is algorithmic. How do we get good model training? But what about the data preparation? A lot of time is spent just extracting, right, transforming all these ETL processes. And if that is usually done on CPUs, this is so expensive. So all the GPU speed up here is not realized in data preparation. And same with visualization. If you're doing high resolution visualization, like we see in many of the astronomy tasks, even there, there's a lot of inefficiency going across these steps in the pipeline. And what Rapids does is give you end-to-end GPU acceleration without ever going back to the CPU. So you move the data once onto the GPU, do all the data prep, model training, visualization end-to-end. And so many times you get 100x or even more speed up because of this ability to do everything there. And the idea is not just to have deep learning methods in Rapids, but also the traditional machine learning methods. Right, so if you're using scikit-learn, it's literally drop in to use Rapids and get all this speed up. And all the data frame analytics, like your favorite data frames, whether it's pandas and other frameworks you're using to process large-scale data, you can now bring that to the GPU very effortlessly. And graphs are, again, very popular in so many domains, so the use of that. And finally, also visualization tools. So all this now being done end-to-end and having infrastructure to do that well. There's lots of real-world use cases. XGBoost is one of the most popular AI methods. And the having speed-ups there with Rapids has been very effective in many of the industry use cases. Yeah, so I want to conclude here by, where I gave you an overview of where deep learning is today and how we want to think in broad strokes of where the field is headed next. Unsupervised learning, better design of priors and more robustness, and better task design and focusing more on adaptivity and guarantees. So then I showed you about use of tensors and TensorLi as a framework that you can easily design better neural network layers, replacing the matrix operations, getting more compact models, but still better performance, better robustness, and generalization. And I also talked about the MESHFREE-FLOWNET that can do super resolution. So starting from low resolution, do the super resolution very effectively because it incorporates the physical constraints, but it also removes the resolution dependence and learns the model to be resolution free. And this then helps us tackle this challenging problem in turbulent regimes. And lastly, Rapids is a great open source data analytics tool. Any machine learning at scale inevitably requires data cleanup and visualization. So I encourage you to try this out as a way to get great speed ups. Thank you.
Thank you, Anima. It was a great talk. And we have 7 minutes for questions. So please go ahead, unmute yourself and ask your question. So I have one question for Rapids. All the tools that you have developed for this platform, are they open source?
Yes. So it's Apache open source, and there's a very vibrant community online. There's Slack, there's lots of notebooks available. So, and the team is always there to be supporting and helping people if there are any issues, and also contribute to the community.
Okay, so if, for example, one of the researchers presenting today was interested in deploying this at a local cluster, is it possible to engage with NVIDIA to deploy these resources on their?
Absolutely. So I know this is available online, and you can start with the self-help and see, and there is Slack, and there is all the Stack Overflow. So if you're running into issues, there's lots of ways to contact the team.
Thank you. Any other questions?
Hi, this is Phil. I'll ask a question. So we saw in Tom's talk about kind of GPU developments that there's some work towards, let's say, reduced bit precision and sort of compression. And bit precision optimization is a little bit different, especially on a GPU. I was wondering if you can talk a little bit about, plans or ideas for including, reduced bit precision in your networks.
Yeah, that's a great point, right? Like there are multiple ways to compress the network. The tensors is a much more global way, right? Because we are replacing entire layers. And then the mixed precision has a way to now ask, okay, which layers require higher precision and which ones don't. And the AMP tool, which is the automatic mixed precision, can greatly speed up and discover how to do these quantizations effectively. And now it's native in PyTorch, so you can directly, and it's also in TensorFlow, it's native. So you can directly enable it there. And so what I see that is, right, the main aspect to consider there, the technical concept is, what about like gradient instabilities? Because once you reduce the precision, sometimes the gradients become, can explode or diminish. So to do that, usually better architectures are already more robust, right? Like, so if you're doing ResNet versus just a standard feed-forward network, the ResNet is more resilient. So it also depends on the architecture, on how effective is AMP. So in terms of the optimization methods, we have a new method called MADAM, which is multiplicative ADAM. And what it does is it directly trains the model in low precision. So and it does that in a logarithmic representation. So the idea is it's much more efficient to now store our numbers in the logarithmic scale rather than even FP16 or FP8, right? So the idea is this is now increasing the dynamic range of our network. So you can go as low as 4 bits in many of the challenging language tasks. And this is something we are actively working on. So I think this co-design of the optimization method with the requirement of quantization together is an exciting area.
Okay, thank you.
Okay, great. Time for one last brief question. If not, then let's thank Anima again for this great talk. Thanks for being with us, Anima.
Thank you.